Look at this! Isn't that pretty? A friend sent me this video of a soap bubble rainbow, and I was completely mesmerized by it. I've seen this a few times before, but I've never really looked at it closely. And it turns out there's some really interesting physics going on here. Let's have a look. The reason that this is so mesmerizing is that these rainbows seem to be made of actual soap bubbles, but they're not. If you look closely, you can see that it's just a thin film of liquid in between the two surfaces. So, what's going on here? Well, when light hits the surface of the film, some gets reflected from the top surface like this, and some gets transmitted into the film and then reflected from the bottom surface and exits the film again like this. Now, depending on the thickness of the film, the light that went through the film will either be in phase with the light that just reflected off the top surface, or it will have picked up a phase shift of 180 degrees. In other words, if the film is thin enough, the light waves will line up like this and add up constructively. If the film is a bit thicker, then the light waves will look like this and cancel each other out destructively. What you see in this image here is the result of this constructive and destructive interference. The areas where the film is thinnest, the light comes out in all directions, and the thicker parts of the film, the light is canceled out. So what we see is basically the places where the film is thinnest. But why do we see a rainbow? For that, let's look at a soap bubble. A soap bubble is a sphere because that's the shape with the smallest surface area for a given volume. That's why liquids form spherical drops. Now, if the film is very thin, like in this example, it's only one wavelength of light. So the light coming out of the top and the bottom of the film will interfere destructively and you won't see anything. But if the film is a bit thicker, say 3 wavelengths, then the light coming out of the top and bottom will interfere constructively. This happens for a range of thicknesses that are integer multiples of the wavelength of light. For white light, which contains all colors, this means that the constructive interference and therefore the rainbow only shows up for very thin films. This is why you need a very thin layer of water on a soap bubble, just a few hundred nanometers, to get this effect. And since the index of refraction of water is higher than that of air, the light gets reflected at the top surface as well. And the combination of the two makes the rainbow more colorful and brighter. So next time you see a soap bubble rainbow, remember, it's not actually made of bubbles, but just a really thin film of water. And it's this film being just the right thickness for certain colors of light that makes them so beautiful. If you also love science and tech stories, consider subscribing to my channel. And if you enjoy reading, so if you want to learn something new, thanks for watching. See you tomorrow!